Here's problem number 4 on the sample test. A block of mass m equal to 2 kilograms is held in equilibrium on a frictionless incline of an angle theta equal to 60 degrees by the horizontal force F as shown. Determine the value of F, determine the normal force exerted by the incline on the block, and if F were removed, how far would the block move in 1 second? To approach this problem, what we really need to do to start off is make a really good Freebody diagram. So let's envision what we have. We have a block on the incline, and we know that gravity is pulling down straight down, but we can break it up into two components, one down the incline equal to mg sine theta, and one into the incline equal to mg cosine theta. While we're doing this, we're trying to conform to an x and y, where x is along the incline, y is perpendicular to the incline. We also have an F force, which is coming straight out like this. And then we also have a normal force, which is perpendicular to the incline like this. All the forces are cooperating with our x and y, the components of gravity and the normal force, except for this F force. It's not cooperating with x and y. We need to break it up into two components that conform to x and y. In particular, we need a component that's going up the incline and one that's going into the incline like this, such that this is a right angle right there. The question is, what are these components? Are they sine or cosine? Which one? Well, if I look at the geometry of this triangle, I know I have an angle theta right down here in the corner here. And if I look at the same geometry, I'm going to have the same angle of 60 degrees right in this triangle right here. So truly, my component adjacent to that angle is going to be F cosine theta going up the incline, and my component going into the incline is going to be F sine theta. This Freebody diagram is looking pretty messy here, so let's see if we can redraw it again with just our components in the x and y directions. So I have this block here. I've got a component of gravity going down, which is mg, oops, didn't want to do that, let's go back, mg sine theta. I have a component of gravity which is into the plane, which is mg cosine theta. I have two components of F, one going up the incline, which is F cosine theta, and one going into the incline, which is F sine theta. The reason it has different sine and cosine from the gravity is because the F force is going horizontally, where gravity would be going vertically, and that's why these components broke down differently, this being our theta here. And then we have one more force, normal force, like this, which is offsetting the two components in the opposite direction, the F sine theta and the mg cosine theta. And all of this, we have an acceleration of 0. So everything is balancing out, and that is our Freebody diagram for this situation. So I want to use this to figure out, first of all, what the value of F is. Let's look in the x direction. Summation of all the forces in the x direction should be 0 because it's not accelerating. And I have a F cosine theta going up the incline and an mg sine theta going down the incline. So it must be true that F cosine theta is equal to mg sine theta. Divide both sides by cosine theta, so F is equal to mg times the sine of theta divided by the cosine of theta, which would be equal to mg tangent theta. Alright, I know all these quantities. The mass is 2, g is 9.8, and theta is 60 degrees. So this is 19.6 times the tangent of 60, 33.95 newtons. Alright, so that's my F force, and that is the answer to part A. For part B, let's look at the summation of all the forces in the y direction. That should be 0, and that's equal to the normal force minus mg cosine theta, and then minus F sine theta, because they're in opposite directions. I could define either direction as my positive direction, because it's equal to 0, one against the other. But I've set it up this way. So my normal force will be equal to mg cosine theta plus F sine theta. This is going to be equal to 2 times 9.8 cosine 60 plus 33.95 sine 60, and that is equal to what? $39.2 newtons. So that is our end force, if I can ever write a 3 here, our end force, normal force of the surface acting on the block. For part C, we were asked what would happen if we removed the F force and just let it accelerate down the incline. So in this case, the only force acting down the incline would be the mg sine theta, theta being 60 degrees, and so that would supply our only source for the acceleration down the incline. If I wrote Newton's second law for the action in this x direction, I would say the summation of all the forces in the x direction is equal to ma, and that would be equal to mg sine theta. Now in this case, the m's would cancel out, and so I'd get that the acceleration is just equal to g sine theta, so that would be 9.8 times the sine of 60 degrees, and that's going to be equal to 8.49 meters per second squared. Nice to know. I've always wanted to know that, but the question is, how far will it move in 1 second? So, it's a kinematics problem. I have constant acceleration, 8.49 meters per second squared. We're going to start from rest, so our initial velocity is 0. And our time is 1 second. And we want to find our displacement, delta x. So there we have it. We have 3 kinematic variables. As for the fourth one, displacement will equal initial velocity times time plus 1/2 acceleration times time squared. And in this case, the initial velocity would be 0, so that term is 0. So we have that this is 1/2 times 8.49 times 1 second squared. So it's going to be 8.49 divided by 2, 4.24. I still had that number in my calculator, 4.24 meters. So it will move 4.24 meters down the incline in 1 second.